Greetings everyone, and welcome to the next video in my lecture series on differential equations. We are still working on Laplace transforms, and this video details what happens when we have translation on the s-axis. So you can see that I've already written that if the Laplace transform of some function f of t is equal to capital F of s using our standard notation, then for a real, so a is just some real variable, then the Laplace transform of the product of that function times e to the at is equal to f of s minus a. So why would that be? Let's take a look. If we take a look, if we write out what the Laplace transform of f is, oops. So Laplace transform of just some function f of t is equal to the integral from 0 to infinity of e to the negative st f of t dt, and that's equal to capital F of s. If we then look at the Laplace transform of this product, e to the at times f of t, that's just going to be the integral from 0 to infinity of e to the negative st, e to the at, f of t dt. But we can rewrite that as the integral from 0 to infinity of e to the negative, and now we're going to take those two exponentials and factor out the t and write it as s minus a times t f of t dt. And so the only difference between this definition right here and the original definition of L of f of t is that we've replaced e to the negative st by e to the negative s minus a times t. So let's write that down. So this is identical to the Laplace transform of f of t, except that s has been replaced by s minus a. And so we can say that this is the same as f of s, except that instead of f of s, we're just going to write s minus a. So this is just f of s shifted to the right by a is our variable, units. So how do we use this property? This means that if the Laplace transform of, let me do a bit of bracket here, t raised to the power of n is equal to n factorial over s to the n plus 1, then the Laplace transform of t to the n e to the at, in other words, our f of t is t to the n, like so, and the e to the at will just provide a shift in s. So let's write this as n factorial over, and instead of s, normally it would just be s raised to the power of n plus 1, but now it's s minus a raised to the power of n minus 1. Similarly, if we have a Laplace transform of cosine of omega t. We found earlier that it was s over s squared plus omega squared. Then the Laplace transform of e to the at cos omega t is going to be equal to, normally we just have s over s squared plus omega squared, but we're going to take every single instance of s and replace it by s minus a. And so where we had s and s squared in the original Laplace transform, we now have s minus a and in the numerator and s minus a squared in the denominator.